This will begin a lesson on our weak acids, looking at a couple of opportunities to calculate the concentrations of a weak acid, pulling out pH. Some of the tool pages we have out, I have my notepad open to page 7. The title here called Weak Acids we'll be filling out together, coming from our Chapter 16, Section 6. I also have in front of me my Appendix D in my just a helpful tool page that we're going to need access to. And I have my calculator out and handy. So our lesson on weak acids. Recall from our previous lesson that the word strong means 100% dissociates and there is no equilibrium that sets up. However, a weak acid does not dissociate in water completely. When I think about the term weak, I think equilibrium setting up between the conjugate pairs. It's an equilibrium problem through and through, setting up our values for hydrogen ion concentration from an ice chart. If equilibrium is established, we set up something known as an equilibrium constant, and for acids that will be known as a Ka. Notice now I have a double arrow representing any weak acid, Ha, in equilibrium with the water molecule producing hydronium, and a negative conjugate base we'll just label as A negative. If I think about the equilibrium process, we could set up an equilibrium constant, and I can use a generic letter for equilibrium constant, knowing that eventually we'll put this into a Ka term for acid. But to put it into last chapter content first, we would see that it would be the concentration of hydronium ion, H3O positive, times the concentration of A negative, the conjugate base, set over the molecular form of our acid, Ha, and recall that pure solids and pure liquids drop out of an equilibrium value. That water there gets dropped out, and we set up an equilibrium products of ions over molecule, products over reactant, dissociated form over the associated form, broken apart, put over the left together. This is known as an expression of an Ka. It is called the acid dissociation constant. Every weak acid has its own unique value for an acid dissociation, and we recognize that's the magnitude of the number that we find interesting. Our Appendix D lists for us alphabetically some of our more common acids. Acetic acid, given our formula of HC2H3O2, we see a Ka value 1.8 times 10 to the negative fifth. That number is very small, indicating that acetic acid is a very weak acid. Compare that to arsenic acid. Arsenic acid, a triprotic acid. I see a series of Kas representing one for each of the ionizable protons. A little bit stronger acid, it's a larger Ka value. So Kas are an equilibrium constant. They're a number. There's no unit. It's the magnitude of the number that we find interesting as a chemist. Our Appendix D gives us the listing at 25 degrees Celsius. That listing, and I've just run off an Appendix D for your convenience, is a test-taking tool page, so you don't have to flip to the back of your book each time you need to look up a number. We know the magnitude of the Ka tells us how strong or how weak our ionizing proton is. Now remember, weak acids set up equilibrium. When I refer to how strong or how weak, I'm referring to how weak a weak acid is or how strong a weak acid is. Strong acids, and there were 7 of them, HCl, HBr, HI. Those are our binary compounds. We had H2SO4. That's our diprotic. We had HNO3 called nitric, and a couple of chlorines. We had HClO4 and HClO3. 1, 2, 3, 4, 5, 6, 7. 7 strong acids that do not have Ka values. So you can see the vast majority of acids, things that start with H and ionize, will have a Ka constant. Strong 100% dissociates. Let me list those names one more time to hopefully stick in your mind. Hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, chloric acid do not have Ka constants. I will not be able to look up hydrochloric acid and find it on here. It does not have a Ka constant. It 100% dissociates, no equilibrium. Now, to the tune of everybody else, you will find a Ka value. Weak acids have a Ka. That doesn't mean that all acids are created equal when they set up an equilibrium constant. That's what we're referring to by the magnitude of the Ka. The larger the Ka value, the stronger the weak acid. It's favoring the product side of our equilibrium. The larger the number, the more we produce product, the ions in our equilibrium. The smaller the number, the more we favor the molecular form. We're going to be asked to calculate Ka from pH or pH from Ka problems, and as we begin to do that, we know that Kas are very small numbers. They're favoring the molecular form of our organic or inorganic acid. So if the Ka is small, we always begin by writing the major species. Okay, that didn't come out very neat. Species. What I'm saying there is figure out what the chemistry is. What are the reactants and what are the products, and begin to write about them and determine what acid am I going to be looking up for my Ka chart. It always starts with an equilibrium problem right from the start, where we're trying to determine hydrogen ion to find the pH of our system. We compare Kas and Kws to determine if a solution will end up to be acidic. Now let's put this into an example. Let's suppose we prepared a 0.1 molar solution of a weak acid known as formic acid, one ionizing proton. We measured its pH using a pH meter and found that to be 2.38 pH units at 25 degrees Celsius. Always begin by showing the chemistry. Write the major species going on in this equilibrium problem. Any weak acid will ionize to release a single proton. Formic acid, HCHO2, an organic acid, when it ionizes, lets go of a single proton, and we're left with something called the formate ion, CHO2 -1. Remember the nomenclature, ic came from ate when we name acids. Formic acid becomes the formate polyatomic ion. Now, what we know is the initial concentration of this weak acid was 0.10 molar. We then measured the pH, and we can think about what we also know. 0 concentration molar units for the two ion products, H plus, and the formate, HCO2 negative. After equilibrium is established, we plunk in that pH meter, and we're finding pH to be 2.38 pH units. But what we can actually pull from that is the equilibrium concentration of the hydrogen ion by taking 10 raised to the negative 2.38 units. Again, just a little pH problem. So with our calculator, we could go 10 raised to the negative 2.38, and we can find the hydrogen ion concentration at equilibrium. This is reading 0.004168. Let's just take 2 decimals, 0.0042 molar units. Now what that means is I now know at equilibrium from knowing its pH. 0.0042 is the concentration of hydrogen ion. Sorry, we have to squeeze this in. At the equilibrium. What I also know, since this ion produces the same quantity, the stoichiometric ratio is 1:1, by reading how many hydrogen ions are produced, I now know how many formate ions were also produced at equilibrium. Since it's a 1:1 ratio, for every 1 hydrogen ion I produce, I make the same quantity of the negative called formate. What I can also tell is how much of this had to be the reactant here consumed or used up to produce our product. So I know that products get made to a tune of positive 0.0042, and that reactants get used to the tune of 0.0042 molar. So if I started with 0.1 molar of my original molecular form of the acid, and I used 0.0042, at equilibrium, what's remaining, 0.0958, why don't I say 0.096 molar units. We now have the equilibrium concentrations of all major species in our ionic form and in molecular form, and we're ready to set up a Ka. Ka is just simply an equilibrium expression of products over reactants. Our product, hydrogen ion at 0.0042 molar, times the concentration of the negative ion, 0.0042 molar. Instead of writing it twice, I'll just put squared at the top. The same number multiplied by itself, I'll just denote that as 0.0042 squared. Set over the equilibrium concentration, 0.096 molar of the acid. And let's hit for our Ka constant of formic acid. 0.0042 squared divided by 0.096, and we get a value of 1.8375. How about 1.84 times 10 to the negative fourth? Again, no units, it's a number giving us an indication of the strength of our weak acid called formic acid. To review, we were given the initial concentration of our acid and a pH reading found at equilibrium. We used the pH to determine the concentration of the hydrogen ion, and we did that with our expression 10 raised to the negative pH. 10 raised to the negative pH found for us not only the hydrogen ion concentration, but it also found for us the formate concentration. We subtracted that quantity to find what was remaining of the original reactant, and we put that into an expression of ions over molecule, product over reactant, dissociated over undissociated form. And we found a Ka constant, 1.84 times 10 to the negative fourth. What percentage of the acid ionized in this 0.1 molar solution? What percentage ionized? Well, the ions that came out, 0.0042 molar, compared to the original concentration of 0.1 molar, multiplied by 100 to express its percentage. What percent ionized? Well, let me just kind of put that into a general formula for us. The percent of ionization is equal to that molarity of the hydrogen ion we found at equilibrium compared to the original acid. Instead of writing out formic acid, I'm going to write that out as just a general acid formula in the initial amount expressed as a percent. Percent ionization. How many ions did we find at equilibrium compared to the molarity that we started with initially? So back to our problem up above, we found 0.0042 molar units of our hydrogen ion at equilibrium divided by the original value of our acid, 0.1, expressed as a percent, gave us 4.2% ionization. That's a pretty small ionization arrow. What we're referring to is the vast majority of our equilibrium is lying to the left. About 4% of the molecules have ionized to give us H plus and CHO2 negative. If Ka is quite small, and it was to a magnitude of a -4, it's a small number, there's some things that we're going to assume. Here are some assumptions we can make. If Ka is very small, a number far smaller than the number 1, we know that the equilibrium lies far to the left. That means it's favoring reactants favoring the molecular form of our acid, favoring the reactants, and that the initial concentration of HA will essentially be the same number at equilibrium, essentially be the same number. Up above, 0.1 molar was our initial concentration. It changed slightly to 0.096. Is that a significant enough change to cause us to do complex math, or would we have gotten close to the same number had we just kept this bottom number at the original value of 0.1? If we make the assumption that Ka is small enough that this subtraction would not significantly change our answer, we can eliminate the need for the quadratic equation. What we are now introducing is something called the 5% rule. When finding percent ionization to check the assumption, the rule says, and it's a general rule chemists abide by, that if I find X to be less than 5%, I can toss out the quadratic equation. If it's more than 5% ionization, I have to use the quadratic formula. When I come back up above here, let's make sense of this 5% rule. I'm going to go back up and recalculate 0.0042 squared, but instead of using 0.96, the difference here from the ice chart, instead of using that, let's see what we would have found had we kept the original value of 0.1. 0.0042 squared divided by 0.1 gives us 1.76 times 10 to the -4th. It's a value that is different, but is it significantly different? It's getting pretty close. That number here, we said it was 4.2% ionization. It's getting close to the 5% rule. You can see the closer you become to 5%, the more the numbers are going to change. But as a chemist, we've agreed upon what's 5%. If it's 5% ionized or less, we do not have to subtract out from the original value. If we find more than 5% ionized, we do have to perform an ice chart. We'll come back to this over and over, the 5% rule. Let's take another example. Another one, it reads, niacin is one of our B vitamins, a vitamin B, and it has the following molecular structure. Let's draw this together. We're going to draw a 6-sided carbon ring, but in one of the corners we're going to place a nitrogen, and a nitrogen has a pair of lone electrons at the top. 1, 2, 3, 4, 5, 6. It's an aromatic compound, which means it has alternating double bonds. An aromatic ring, like a benzene ring. And hanging off this corner of our structure is a COO, an organic acid with an ionizing proton right there. Vitamin B is an organic acid. It will ionize this particular hydrogen ion. Now, we've drawn the structure and showed it's a monoprotic acid, and it will release this one hydrogen ion when it's dissolved in water. If we started with a 0.2 molar solution and had a pH of 3.26, what percentage of the acid is ionized in solution? And calculate the Ka. For any weak acid, instead of redrawing or even putting in a molecular form, I'm going to simplify and just show niacin written as HA. Any general weak acid, HA, and I'll call that the weak acid niacin. When it dissociates, it sets up an equilibrium between a proton, hydrogen, and its conjugate base, I'm going to call that A negative, which would be the same structure I drew here, minus the hydrogen, now carrying a -1 charge. The Cu will become COO, -1. This is a more simplistic way just to keep number tracking easy. Initially, we were given 0.2 molar HA. At equilibrium, we found a pH unit of 3.26. We know that we can use our pH 10 raised to the negative pH to find the hydrogen ion. Well, let's hit for that and see what we find. 10 raised to the negative 3.26 gives me a hydrogen ion concentration of 5.495. Let's just say 5.5 times 10 to the -4th molar units. At equilibrium, the hydrogen ion concentration is 5.5 times 10 to the -4th molar units. Not only is that the hydrogen ion concentration, but since it dissociates to give equal amounts of acid and the conjugate base, I also know this guy to be the same value. Before we go through and decide, do we have to complete the ice chart, let's check the 5% rule and decide, is it worth finishing out the ice chart, or can we go straight with what we have to calculate the Ka? So let's check the percent ionization. Are we going to fall under the 5% rule? The value we found of 5.5 times 10 to the -4th molar units set over the initial concentration of 0.2 molar expressed as a percent. Are we under 5%? So I have my value still on my calculator screen, 5.5 times 10 to the -4th units, divided by the original value of 0.2, expressed as a percent, and I am well under the 5% rule. This percent is 0.27% ionization. Well, that number is quite small under the 5%. In other words, I do not have to complete the ice chart. I can go straight to calculating my Ka constant value, the equilibrium constant for niacin. Products over reactants. We would recognize that subtracting out such a small number from the 0.2 does not significantly change that value. It's not worth doing. Products over reactants, 5.5 times 10 to the -4th molar units. Square the top because those are the same value. Divide by the original molecular concentration of 0.2, products over reactant, and let's find the Ka for niacin. We would hit 5.5 times 10 to the -4th squared divided by 0.2, and I find on my calculator 1.51 times 10 to the -6th. the Ka for niacin. And no units, it's a number showing that niacin is a very weak acid. The 5% rule allowed us to judge that subtracting out such a small number would not significantly change the equilibrium value of this weak acid. That math isn't worth doing. It would not significantly change the value of Ka. Chemists have agreed upon 5% or less. Toss out the ice chart. We've just been given pH to calculate Kas. What if we are given Kas and asked to calculate pH? Kind of the opposite direction with information. We'll review 4 steps and kind of go through those steps using examples. Step 1 says we should always write the chemistry. Write the ionization equilibrium for the acid. From there, we'll be able to determine the equilibrium constant expression. We'll find the concentrations that are involved using an ice chart and substitute those values in from our equilibrium constant expression. Using a Ka, calculate a pH. Let's begin with an example. Calculate the pH of a 0.2 molar solution of hydrocyanic acid. We would use our value found in Appendix D for HCN, hydrocyanic acid. Not cyanic, hydrocyanic acid. Of course, no, I'm not seeing it. Oh, here it is, hydrocyanic, HCN. 4.9 times 10 to the negative 10th. And I know that was typed there, but I wanted to show you where it was found. If that information is not provided, we know how to find that using our Appendix D. Hydrocyanic acid, HCN. When it ionizes, it sets up an equilibrium with H plus and Cn negative. It dissociates in water. The equilibrium expression, Ka, would show hydrogen ion, H plus, times the cyanide ion, Cn negative, all over the molecular form of our acid, HCN. This expression is equal to the Ka. We know that to be 4.9 times 10 to the negative 10th. That's what we know so far. Okay. Now I'm going to do some work over here. So I'm going to rewrite my equation. I should have written it here where I had more room. The initial concentration of our solution, the molecular form, and I'm just thinking about what we know. This is 0.2 molar, or 0.20 molar of HCN. We don't know. We'll just kind of finish this ice chart, I guess. What we don't know are the equilibrium concentrations of H plus and Cn negative. We know reactants get used, products get made, and it's all stoichiometry of 1 to 1 to 1. So minus X for the original reactant, plus X for the original product. So at equilibrium, 0.2 minus X, our value of the original molecular acid, the value of X for both ions. There's our ice chart. Our original concentration of the acid, 0.2 molar. We know the equilibrium constant, 4.9 times 10 to the negative 10th. We're going to sub that in and pull out the value of hydrogen ion, what we called X. Now, what I would recommend, assume the 5% rule, and then we can go back and check if our assumption was correct. Assume it first, and then go back and repair if needed. So in other words, when I look at this value, 4.9 times 10 to the negative 10th, that's my Ka. That's going to be equal to the products, x times x. Why don't we just write x squared? And instead of writing 0.2 minus x and dealing with the quadratic equation, let's drop this x out. Let's assume the 5% rule, and then when we find hydrogen, we can do a quick check. And if it ends up to be greater than 5%, we'll have to back our bus up and go back to quadratic equation. But why not test it first and save all of that initial algebra? Let's pull out x. (4.9) e negative 10. The Ka, I'm going to cross multiply that with 0.2 molar. Now that's equal to x squared, so I'm going to square root my answer, and I find the value of x to be 9.9 times 10 to the negative 6 molar units. And remember, that's the hydrogen ion concentration. Before we continue, let's check the 5% rule. Let's compare the answer we just found to the initial concentration and see if our assumption is all right. So at equilibrium, we found hydrogen ion 9.9 E negative 6. Divide by the original concentration of 0.2 and express that as a percent. Oh, look, we're well beneath 5%. This assumption was fine. If it came out greater than 5%, back the bus up, got to do all the algebra for quadratic formula. But this number came out to be 0.005. I mean, that number is significantly small. Very safe algebra to toss out the ice chart. We're not done. We have what we need to calculate pH, but we have a little more work to do. We have to take the negative log of hydrogen ion to find pH. So I'm going to hit negative log of our x, 9.9 E negative 6. Negative log of the hydrogen ion concentration gives us a pH value. Always 2 decimal places. pH 5.00 units. The pH of our hydrocyanic acid is 5.00. Let's review the process. We found an equilibrium for a weak acid. Using Appendix D, we simply looked up its constant, 4.9 times 10 to the negative 10th. We set that constant equal to the concentrations of both ions. We called them both x. That's why we write x squared. Over the original value from the ice chart, the original value of the acid. Checking the 5% rule, we found that it was all right to do that, tossing out the minus x, and pulled out x, which represented hydrogen ion, the column right here. And remember, this is what we need to calculate pH. At equilibrium, we need to know the hydrogen ion concentration to negative log to pull out pH. Let's try another practice. We're going to use Ka to calculate percent ionization. If we have a 0.1 molar HF solution, hydrofluoric acid, 0.1 molar HF, all we're being asked to do is calculate how many ions come out. Well, we have to go to work finding a constant, a Ka constant for that acid, hydrofluoric acid. 6.8 times 10 to the negative 4th. Hydrofluoric, 6.8 times 10 to the negative 4th. When hydrofluoric acid dissociates, it sets up an equilibrium with its two ions, H plus and F negative. Why don't we call H plus X? The value of the negative ion would be the same. We'll also call it X. And when we set up our equilibrium, the initial concentration of our acid is 0.1. Using the Ka expression, 6.8 times 10 to the negative fourth is equal to the products, x squared, over the initial concentration of 0.1, and let's solve for x. (6.8) E negative 4 times 0.1 is x squared. So let me square root my answer, and I get 0.0082. Remember that x represented hydrogen ion at equilibrium. To find the percent ionization, we want to compare hydrogen ion to the original concentration. Equilibrium set over the original value. Its percent ionization, 0.0082 divided by the original value of 0.1, expressed as a percent. Oh boy! 8.2% ionized. Was that good math? When I see percent ionization coming out that large, that's telling me I am not allowed to toss out the quadratic formula. When I set up x squared over the original value set equal to Ka, and I solve for percent ionization, 0.0082 set over the original 0.1, boy, that number is too large. If I had to go back and calculate pH, I'd go back and use the quadratic equation. I'd have to, and I'd have to go all through that to find the correct value for the pH. Too big, 8.2, too much of it's ionized. I'm not allowed to just toss it out. Let's see what happens with the same acid, but we dilute it. We're going to dilute it from 0.1 to 0.01. So we're diluting it by a factor of 10. Same Ka constant, 6.8 times 10 to the negative fourth. But instead of a 0.1 solution, we've diluted it to a 0.01 molar solution. And what happens to that value? So let's hit for this. We have Ka of 6.8 E negative 4 times 0.01 is x squared. So I square root my answer. And now I'm seeing 0.0026. Compare that to our original concentration of 0.01 expressed as a percent. Holy mackerel. Now I'm at 26% ionized. By diluting it with water, I'm significantly causing it to ionize even more. 8 goes into 26 roughly 3 times, and 8 times 3 is 24, but give you a rough idea. By diluting it with a factor of 10, we've increased the molecules being ionized significantly. It really is nothing more than Le Chatelier. Think about our original equation. And I'm just going to turn my paper a little bit sideways so I have some more room to write. If HF placed into water sets up an equilibrium, HF dropped into water. What if we add more water? That's Le Chatelier's principle, isn't it? If we increase the concentration of a reactant, we're going to force that reaction to establish equilibrium again and relieve the stress. It's going to shift to the right. Shifting to the right drastically increases the number of ions. We can see that with a percent ionization. By adding more water, we increase the number of ions by about 3-fold. Le Chatelier's principles, we have more particles on the right side causing a dilution to increase the number of ions. So we see that shifting from left towards right. Dilution caused the reaction to shift in the direction of the ions or the number of particles, or shift right, because it counters the effect of decreasing concentration of those particles. We shifted to the right, causing the dilution to go toward the ions. Let's do one more practice before we stop. More practices. Earlier we found the percent ionization of niacin, Ka. Niacin, we drew that structure back here. Here's the niacin molecule called vitamin B, and we set up a little ice chart. We found that to be 1.5 E-5 in a 0.02 molar solution. And we found it to be 2.7%. If I remember right. This value we found to be 0.27%. Let me adjust that correctly into the note pack. The answer from an earlier problem working with niacin in a 0.02 molar solution, we found that to be 0.27%. Let's take a peek as we begin diluting that to the percent ionization. When would it be okay to toss out the quadratic equation following the 5% rule? So let's compare. Again, niacin has a Ka of 1.5 times 10 to the -5th. The hydrogen ion will represent by the value x, and the negative ion also represented by the value of x, so I just write that as x squared, over the new concentration value of 0.01. Let's pull out x. Take the Ka constant, 1.5 E-5, times that concentration of 0.01. Set equal to x squared though, see that? It's x squared, so square root your answer, square root your answer, and here's our value of x. We have 3.87 times 10 to the -4th molar units, the value of the hydrogen ion. Compare that to the original concentration and find the percent ionization. So this value we found is the hydrogen concentration at equilibrium. We want to know percent ionization, so we take this value and simply divide by the original 0.01 molar, and we'd like to know a percentage, so times 100. 3.87% ionized. By diluting the solution, we've caused more ions to come out. We went from 0.27 in a concentrated solution to 3.87 by diluting it. Le Chatelier says adding more water forces more ions out of solution. Diluting this even more to 0.001 molar, 1 times 10 to the -3. Let's calculate what happens to the percent ionization as I dilute to 0.001 molar. The constant, 1.5 E-5, times our 0.001 concentration of our original acid. Square root that to find the x value. And x here is 1.22 times 10 to the -4th molar units. That's our concentration of hydrogen at equilibrium. To find percent ionization, we compare the hydrogen ion at equilibrium to the concentration of our original acid. We'll divide by 0.001 and express it as a percent, significantly increasing the number of ions by diluting the solution. The moral of the story: when we fall below 5%, it's okay to toss out the ice chart, but we see some things that are influencing whether or not we're allowed to do that. The magnitude of the Ka certainly influences the extent. The original concentration also influences the extent at which ions form. We must check the 5% rule to decide if it's okay to toss out the ice chart. Less than 5%, make the math easy. I would go on and simply negative log the hydrogen ion concentration to find pH. However, when I set up my equation, checking my 5% rule, and it falls greater than 5%, as in the last example, I have to back up, creating an ice chart, solving with quadratic equation to find the equilibrium concentration of hydrogen to therefore pull out pH. Let's pause here. The next lesson will pick up with polyprotic acids.